learn in linear algebra are simply properties of matrices. Now, these matrices, you know what they are composed of. Yeah, so these are just like diagrams or representations that have rows and columns where there are numbers inside. You know what that means. So you have matrices that are 1 by 1, you have 2 by 2, you have 3 by 3. So let me just give you this Hawker list here. So I'll just be running through your course outline, then give you an example on everything that they're implying. Yeah, so you know what matrices are about. So here we're just going to say matrices. Okay. If this guy is not writing. Okay. Okay, yeah, so I want to discuss matrices and all the properties. So this is just like a refresher part where you have to remember everything about matrices, because from topic 2 going down, all the theories you're going to learn are going to involve matrices. Yeah, spanning or vector spaces, we're just going to capitalize on this. It's like for those that are doing 2300, it's like how you learn sets in the first topic under real analysis. Then the rest of the course is just you learning things about how sets actually relate, all the properties of sets. So it's one and the same here. This whole course is about matrices. Yeah, so 2200 is a very, very simple course that you can get good grades as long as you're able to retain the theories, explain them, and give a very probable proof whenever you're answering your questions. Yeah, so we say this is just going to be a representation of numbers in rows and columns. You know how they look alike, They give you something like this when you are learning. They give you this. We have, let's say, A and J. If this is OA, let's say this is let's have to N. You have a combination, right? You have this. The arrangement is really not going to be in a way that is special. There is no special way of how we're going to be putting our numbers. Yeah, so of course we'll have other special matrices later on, like the identity matrix, how the numbers are arranged, the numbers that are found inside. There are those two more special things. But yeah, so let me just say this is 1 1. This has to be 1 1 here. The numbering is going to go with the row and the column that you have. So this goes up to, this is row number 1. That's the nth column. Then we go down, we have, let's say, B. This is column number, let's say, M, for instance. Row number M, we don't know what the other rows in between. Then this is column number 1 until we go to the last one, which is going to give us column number M, and then we don't know. So we have row and column. We have our rows, then we have our columns. Yeah, so whenever we are placing a digit or imputing a number, the position is always going to go by row, by column. This is always what we mean. So this small number is a row. So row that it's in, then column. This is very important when it comes to things like finding or transposing a matrix. Yeah, so we know what this is. The second thing you learned is the order of matrix. So the order is the same thing, the number of rows and the columns. So row by column, always. This is the order we're going to follow. Yeah, so if I give you, let's say, this, please don't be bored. I just need to build up from the basic things that you learned. Yeah, so if I give you this, the number of rows here, this is simply the order of this matrix is what? This is going to be a 2 by what? A 2 by 3, right? That's what you're going to get. Tasha, you're trying to say something? Hello, Tasha. Yes, you are trying to say something? Oh, okay. Yeah, so after doing the row and the column thing, you went further and did the properties that have to do with addition and subtraction. So of course, matrices can be added, but there's a condition for addition and subtraction. Yeah, the condition here is that whenever you're trying to add or subtract two matrices, A and B, the order must be the same. So the condition here is that they need to have the same order. The number of rows and the number of columns must match everything. Yeah, that's the only condition. So I'm guessing you don't need an example for that. This is just like pairing things, so this is straightforward. Then apart from addition, we said subtraction is the same thing as well. The order has to be the same. Then when it comes to let's say non-examples, sometimes they can give you non-examples, ask you for non-examples. Yeah, let's say you have matrix A. This is there's a 1, there's a 2, there's a 7, there's 8, there's 10, there's 11. Then there's B is equal to, this is what, 7, 9, 8, and 11. So A plus B, is it possible to get A plus B? Or 2 to get B plus A? Is it possible to do these additions? Chris, can we add these matrices? No, because the order is not the same. Yeah, so the condition is that the orders have to be the same. So for this non-example case, you say not feasible. Yeah, so you say not feasible because the order is not the same. Yeah, different orders. And this is one thing that gets people to get a very good grade in 2200. You have to learn how to explain your answers thoroughly. Yeah. So apart from learning about the orders of matrices, you went further to learn about multiplication, because we talked about addition and subtraction. How about multiplication? Of course, there is no division for matrices, not at your level. Yeah, so multiplication, if you're trying to multiply two matrices A by B, yeah, here we just say this is just supposed to be the same as if you're multiplying A by B. The order here is row by column. Here the order is row by column. The number of columns in the first matrix has to be the same with the number of rows in the second matrix. Then you'll be able to multiply them. Yeah, this, I'm sure you remember this as well. And I should mention here to say under addition, addition is commutative. So I must say here, you need to know this. Matrix A plus B gives you the same thing as B plus A, but A minus B does not give you the same as B minus A. So addition is commutative, subtraction is not. So please take note of that. Yeah. Then here we have multiplication. Under multiplication, guys, is multiplication commutative? Tasha, is multiplication commutative for matrices? If I give you A is equal to, let's say 1, 3, there's a 2 and a 4. Then there's a B is equal to, this is, I'll use small numbers. Let's say 1, negative 3, and let's say there's a 5. So if you check this, it's not, right? Yeah, so this is not the same as B times A, so it's not commutative. Yeah, so you need to know this. Then there's a difference. People confuse this for two matrices. This guy is not true. We're saying this is not true, but we can actually distribute matrices. If you have, let's say, matrix A outside and you have B plus C in brackets, this is equal to, we can multiply A by B. That's going to be A by B, then plus multiply A by C. So we can have this. We can distribute but not associate. Yeah, you notice the positioning. So even if I was to give you this, they give another illustration here. If I give you A plus B, two matrices adding, then there's one matrix outside. It's just going to be A times C, then plus, then B times C. So the order has to be preserved. Yeah, this has to do with us introducing a scalar later on. Yeah, so I am hoping you're able to see the difference here. There is associating, switching matrices. Then there's distribution, maintaining their position, just distributing them. So A times B, A times C. It will give us the same with A times C first, then plus B times C. So this is okay. Then this extends to when you have a scalar. A scalar is just any number, any constant that can magnify or rather reduce your matrix. That's what we call scalar multiplication. Yeah, so if you have, let's say, a matrix A is equal to, let's say, 5, 6, 1, and 0, then there's a scalar C, which is, let's say, a 3, for instance. We can have C and A, meaning the number C is going to affect every element, every entry that you've made in matrix A. So meaning CA is just going to be, there's a C outside, that's a 3. The matrix, that's 5, 1, 6, 0. So you can just magnify this, right? You get your 15, your 3, your 18, and your 0. So this is what we're having. Yeah, so we have scalar multiplication as well as scalar distribution over matrices. So you have C outside being your scalar, you have 2 matrices, A and B. So instead of adding them first and multiplying by C, you can magnify A and B separately, then add them. So you can get this. Yeah, hope this is okay. Then apart from this, there's a part we learned how to transpose a matrix. So here I'm just going to give you the properties you need, right? Yeah, so this is here on scalar. I should mention to say if your scalar is 0, of course your answer is going to be 0. Yeah, so we call this a 0 matrix, where every entry is going to give you what? Is going to give you, is going to become a 0 if you have a scalar of 0. Yeah, so you get a 0 matrix, a matrix full of zeros. Then what do you mean by transpose, guys? If I give you this, Tasha, what do you mean by transpose of a matrix? If I say AT like this, what do you mean? So the rows become the columns become the rows. So Tasha, I want Tasha to answer this one. Hope she's still in the meeting. Let me check. Okay, she's left. Okay. Okay, so Chris iwizi wasonza ile mbachete. So eza bwa nkale bwanje AC then BD te. Yeah, so this is what we're going to get. So the same applies to if I give you 1, 3, 6, then I give you 2, 4, 7. So A transpose is going to give us what? Yeah, so you call them this. So these are the properties. Yeah, so say apart from them just switching the order and you just changing, so the rows become the column become the rows. So 2, 1, then 3, 4. So just pindamula change there. So for the sake of those who are going towards the recording, yeah, then the axioms is just the same thing as we say properties. How can we relate the original matrix and its transpose? So transpose is more like complement. Yeah, it's like when you flip something twice. So there's the first property here is that if you transpose something twice, you get back the original matrix. Is this okay, or Chris, or you need an example for this? You understand what this means, right? Yeah, then we have this guy here to say if you add 2 matrices or subtract them, then transpose, it's just the same as you first of all transposing the first matrix, adding or subtracting the second matrix. It's transpose. Yeah. So ilishamunga complement, might shall distribute complement of a complement plus original set. So it's the same thing. Yeah. Then the other property is that if 2 matrices are multiplying each other, they like this equation because people always forget. This is equal to B transpose, then A transpose. They like this equation from quizzes. Yeah, so it's not, so look at what has happened. So you have to pay attention to the details here. Here it was AB in brackets, their product. After they've multiplied each other, then you transpose the answer. Here we're just saying transpose B multiplied by the transpose of A. Then these two answers, the left and the right, will be the same. So they emphasize to say note that AB, then when you transpose, it's not the same as A transpose and B transpose. Yeah, so please don't forget this part. The B comes first, the transpose of B comes first, then the transpose of A. Then if you have a scalar cannot be transposed, so let's put the scalar to be A, and if you have a matrix and then there's a transpose outside, it's the same as you just multiplying K and the transpose of this guy here, where K is a scalar. K is a number. You cannot flip a number. You cannot change a number. Row, column, as long as it's a 1 by 1, okay, change the same number. So treat a scalar as if it's a 1 by 1 matrix. A matrix that only has one element, right? Yeah, so this is basically what we're having. Yeah, so this is all the properties you need to master on transpose. So they do ask about these guys. You need to swatter them. Yeah. Yeah, so apart from this, any question here, Chris? So there are terms that you need to be comfortable with. The first one we're going to look at is the main diagonal. So if I give you a matrix like this guy here, let's say there's 1, 2, 3, there's 4, 5, and 6, then there's 7, 8, and let's say 9. The main diagonal here are just all those terms. So I'll just say these are all those terms that have, let's say, how can I write? Those guys that have, let's say, 1, 1, let's say 2, 2, that have, when you list all the elements, when the row, the position of the row and the column is the same, those are the guys that we're categorizing to make up the main or the major diagonal. So in this case, we're going to say it's 1, 5, and 9, because this is going to be the same as A is 1, 1. The position of this term here, 2, is 1, 2. The position of 3 is 1, 3. Then this is 2, 1. So we're having this. Yeah, so you notice this is going to be your main diagonal. Some people say major diagonal. Yeah, so main or major will just mean one and the same. Now, there are certain properties that we associate with the main diagonal that we're supposed to know. So here we're going to list them. So the properties are that the first one, we're going to say the main diagonal elements of a square matrix are located from the top left to the bottom right corner of the matrix. So a square matrix is a matrix where the rows and the columns are the same. Yeah, so we have to list them from the top. So we say top right up to top bottom. Yeah, so from the top, so there's a corner here, top right corner to the bottom, to the bottom. We say this guy is going to be what? To the bottom right. Top right, is it? So let's say this. So just this part here. So I don't know if this makes sense, but okay, you get from the top right here, this guy, we stand here, we go in the right, then this guy here, bottom right as well. So this is basically what we are saying. That's what we have. The same thing we discussed. And the second thing is that in a non-square matrix, let's say a rectangular one, the concept of the main diagonal does not apply, since the number of rows is not the same with the number of columns. So this concept is only applicable to square matrices where the rows and the column are supposed to be the same. So if, here I'll say if and only if the rows are not equal to the number of columns, main diagonal does not exist. I'll say does not exist. That's the second property. Then the last one, The last one, we're saying the main diagonal is important in determining the trace of the matrix. The trace is simply the sum of all the elements on the main diagonal of a square matrix. So trace is you just summing up. So I'll give you a formula here. When you sum up all the elements, in the major diagonal, that gives you the trace. Chris, this is okay, right? Do you need an example for the trace? Yeah, so for the sake of those who are going to be watching the recording, we're saying for you to get the trace of a matrix, you just need to add the sum of all the elements in the major diagonal. That's the trace of a matrix. So here we have an example, and this is the notation that some lecturers use. They'll say find the trace of A. They'll write it like this. This means trace, meaning we need to add all the elements in the main diagonal. So elements in the main diagonal, there's a 1, there's a 5, there's a 0. So just add them. 1 plus 5 plus 0. This gives us 6. This is okay now, right? Yeah, so in the trace, trace, just add up the numbers in the main diagonal or major diagonal. Now we've said something about the main diagonal. The main diagonal can only exist for matrices which are square. By square we mean the number of rows is equal to the number of columns. So for those matrices that are not square, they don't have a trace. Yeah, so a trace is very important. Later on you'll see why we need the trace. It will tell us certain things about a matrix before we even start dealing with it. Yeah, the smaller the trace, the more reduced your matrix is. We'll talk about it later on, just right here. Yeah, so apart from this, we need to talk about types of matrices. Yeah, so we talked about the major diagonal. I want to talk about an identity matrix. So when it comes to the identity matrix, we know to say every matrix that we've talked about, whether 2 by 2, 3 by 3, anything, any order that you have, is going to have an identity matrix. But we're mainly going to focus on square matrices, identities. Yeah, so if I give you an identity, this is written as IN, capital letter I, subscript N, then you say the identity of something is always, there's a 1, 0, 0, 0 this side, then there's a 0, 0, there's 0, then there's a 1 here, there are zeros, and so on. There's a 1 here, then there's a 1 at the end. So an identity matrix, like for a 2 by 2, for instance, the identity matrix for a 2 by 2 is just going to be 1, 0, 0, 1. The definition is that all the elements on the main diagonal are 1s and the rest are zeros. That's an identity matrix. A matrix is called an identity matrix if it's a square matrix with 1s on the major diagonal and zeros elsewhere. That's what we call an identity matrix. So meaning for a 3 by 3, for a 3 by 3 matrix, we're simply going to have 1, 0, 0, 0, 1, 0, 0, 0, then a 1. That's basically your identity matrix for a 3 by 3. And these have properties. So every identity matrix has certain properties. Of course, we're going to learn Cramer's rule later on, so we'll need to get this, how to get the inverse of a matrix, to get a cofactor matrix. So we need this. Everything we're doing here is just like building up. So the following are the certain axioms you need to be familiar with. So be comfortable with this term. This just means the same thing as properties. Yeah, so axioms of identity matrices is that when you multiply any matrix with its own identity, the answer you get is the same as that matrix. So this is the same as an identity matrix times any matrix. the answer is always going to be that matrix. So we said multiplication is not commutative, right? But for an identity matrix and any other matrix, it is. Yeah. So A times its identity matrix, it's the same as identity matrix times that same thing. So I can give you an instance here. Let's say 2, 1, 0, 3. When you multiply it, this is a 2 by 2. So the identity matrix is what? 1, 0, 0, 1. This is the same as, you say what? 1, 0, 0, 1. Then multiply with 2, 0, 1, 3. This also give you A, matrix A. Yeah, so you can check this at your own free time, but yeah, identity matrix and any matrix is that that matrix. That's the first property. Then 2, there is some form of uniqueness when it comes to every identity matrix, because every square matrix, let's say 2 by 2, their identity matrix is not the same as for a 3 by 3, and this can easily be explained when you talk about the trace. So the trace of a 2 by 2 identity matrix is 2 because you're adding all the numbers, the ones on the main diagonal. For a 3 by 3, it's 3. So you get that there's a difference because the traces are all different. Yeah. 2 matrices are said to be the same or almost the same if they have zeros elsewhere and the numbers on the middle all add up to the same trace. Yeah, we'll talk about that property later on, but here we just want to say all identity matrices are what? Are unique. So I hope that that is better. Then it's also said that the inverse of a matrix, an identity matrix, is the same as itself, the original matrix. So A inverse can only be equal to A if A is an identity matrix. So that's what I'm basically saying. Yeah, so I know I've not yet done the inverse, how to get the inverse, but I think I should be able to explain it soon. Yeah, we're coming there. Here to just a property. Then the fourth thing. The fourth thing is that also the transpose of an identity matrix is equal to itself. Yeah. Hope that's okay. So how do you check whether a matrix is an identity matrix? Check the inverse, check the transpose. If they both give you the same thing, meaning it's an identity matrix. Then if you add it with a zero matrix, it gives you the so they're saying additive inverse, the additive identity with zero matrix. The identity matrix is distinct from the zero matrix. The zero matrix and the identity matrix cannot be equal because if you say this plus a zero matrix, so I'll just say 0. This is plus, sorry. This will give you the identity matrix. So by zero matrix, we mean all the entries are zeros. So imagine you're trying to add this. Plus. This is going to give you this. You see, right? Yeah. So I know it's obvious, but we need these properties later on in the future. We'll need them for proving certain things. Yeah, then multiply by a scalar, meaning the entries on the major diagonal are going to change. So if you multiply an identity matrix by a scalar, remember an identity matrix, all the entries are zeros except the guys on the main diagonal, they're the ones. So it should be number what? I've been lost track now. It should be number 5 or something. If there's a C multiplying an identity matrix, it means that all the entries here will be C's. And we don't care about anything else. So this is just going to be, a C as well. So something like this. Hello, Chris, are you able to get me? Can you still get me? Okay, so here we're saying if we're having a scalar multiplied by the matrix, the ones on the major diagonal of course have to change because that's a scalar, right? Multiplying this, so they'll change to become that scalar. So if you have a 2 and an identity for 3, this is just going to be 2 0 0 0 2 0 0 0, then with a 2 you have something like this. Yeah, so I emphasize again to say if you multiply an identity and a scalar, an identity and a matrix. Yeah, so if you multiply A and this guy, you still get the same thing, which is A. Provided, remember the rules of addition. So here, sorry, it's addition. Yeah, or even multiplication. So let me just say this is multiplication here, actually, multiplication. So this should be the same as getting the identity matrix, multiplying it by A. We said multiplication is not commutative. It's only possible if the other matrix is what? An identity matrix. So hope you're able to remember this. Then another type of matrix that you're supposed to be aware of is what you call a symmetric matrix. So I'm sure they did mention to say if there are more than two, you say matrices, then matrix meaning just one. So a matrix is said to be symmetric if it's equal to its own transpose. So if you transpose a matrix and it looks the same thing as it was, meaning that's a symmetric matrix. Remember, transpose, we change the rows to be the columns and the columns to be the rows. So it can only be possible if what's on the right is the same as what's on the left. So it's just be symmetric. It mirrors itself, so to say. Yeah, if you transpose it. So a perfect illustration I can give you is if you have e.g., let's say A is equal to, how can I say this, 1, 2, 3. There should be a 2, 3 there. I need a 4 here. The numbers here have to be the same. Then let me put something different here. Let's say 6. Yeah, so when you transpose this, A transpose, that's going to give you, again, it's the same thing. Yeah, 1, 2, 3 is the same thing that you're going to get again. Yeah. Then 2, 4, 5, then 3, 5, 6. Yeah, so that's when we call a matrix to be symmetric. Now these guys have properties. When can a matrix be symmetric? So when can that happen? Yeah, so certain properties for you to make a matrix to be symmetric is that the first thing, we need to consider it to be a square. The number of rows and the columns have to be the same, meaning row by columns. R has to be the same as C. It has to be a square matrix. That's the first condition. Yeah, because we're trying to create a left hand, right hand type of reflection. So that's what we need to consider first. Yeah, it needs to be cut by cut. Then of course, the equality between itself and its own transpose, this has to be satisfied. Yeah. So this is like us looking for things that should be satisfied, or properties, conditions that must be met for us to actually call a matrix to be a symmetric matrix. Yeah. Then here we're saying the symmetry of all diagonal elements. So when we flip the whole matrix, the major diagonal elements are supposed to be the same. In short, the trace has to be the same. So the trace of the matrix should be the same with the trace of its transpose. That's just me summarizing this property here when it comes to the major diagonal entries. So they're supposed to be the same when you reflect it. Yeah. Then if there's what we call symmetric powers. So if you raise a matrix to a certain power, let's say here you have, let's say A to a certain power, let's say K, meaning A has to multiply itself K times. This is going to be the same as if we transpose A first, then let the transpose of A multiply itself K times. The answer should be the same. So this should give us A to the power K. I hope this is clear here, Chris. I hope this is okay. So now K can be anything. So K is just a scalar. Let me just say it's a scalar. So we say A to the power 2, for instance. When you say A to the power 2, we just say A times A. That's what we basically mean. Yeah. Hope that's okay. Okay, then I should say what? Let me say okay, so there's a property here. There's this guy here that we call sum and difference. Yeah, so if you have The sum or difference of two symmetric matrices is also symmetric. Yeah, so if you of two, so here two symmetric. So A plus B, the outcome they're going to get, this guy is also symmetric. A minus B, this guy is also going to be symmetric, provided they're both symmetric. They satisfy the above conditions. Yeah, and the proof that we're going to use here, so the proof, how do we prove this? So I'm going to prove the first one. So I'm going to prove the addition one. Then you can prove the subtraction one. So I'll prove this. Yeah, they'll ask you how do you prove this? So proof. Remember, we've said that if a matrix is symmetric, so we say since, you need to write since A and B are both symmetric, it means that A is equal to A transpose and B is equal to B transpose. Then we're going to add then we're saying since is symmetric, even the transpose is going to be symmetric. Implies that A is symmetric. That's what we're going to get. Now remember, we say this here, A transpose is the same as A, right? So this is the same as A, then this again is the same as B, so this is the same as that, so this is the same as that. They are both symmetric, meaning their sum is also symmetric. So that's how we're just supposed to do it, because A is equal to AT, A transpose, B is equal to BT. So this is a simple proof that we're supposed to write. The same will apply for minus, meaning we're supposed to subtract here. We'll put a minus. Yeah, so this is a simple proof that you need. Yeah, so an example maybe would be, if I give you a proper example. So let's say we have the same thing I gave you, because we say what? Oh, we said symmetric. We said its transpose supposed to be the same, right? Yeah, so I already gave you the one that had 1, 2. This guy here that we looked at here. Yeah, this guy. This is a symmetric matrix. I've already given an example. When you transpose it, it gives you the same as original matrix. Yeah, so hope that's okay. Chris, is this okay? Can we move on to skew matrices? So here we're just talking about terminologies. So the types of matrices now. Yeah, okay. So this is just meant to refreshen everything that you learned in class. I'm just focusing on the key points. I know they can write a lot of notes in class and include some irrelevant things, but I'm hoping that this will just like go directly to what you need. Yeah, so hope this is helping you to revise what you did in class, because I want to reach until we do a reduction, row echelon form. That's what I want. That's where I want to end on today, at least. Yeah, so that we catch up this. So a skew matrix, from the word itself, skew, it just means something that's not symmetric. Yeah, so a matrix is skew metric if it is equal to the negative of its transpose. Yeah, so this is, I need to add a term here. We say skew matrix, skew symmetric matrix. Yeah, so something like this. So we just mean that if a matrix is equal to negative its own transpose, then that's negatively, that's skewed, meaning it's pushed a little bit. This means that each element of the matrix satisfies the relation that the elements you find, because they were supposed to be equal, right? They were supposed to be equal like this. But then we find that every element that was in the original matrix has been negated. So there's a negative in front, meaning it's like we have a -1 as a scalar, sort of. Yeah, this here just explains what we mean by skew matrix. Every term gets a negative. Yeah, so the properties for this, or it's like I give you what, how can I tell you this? If I give you A is equal to, this is a perfect example, 0, 2, then there's a -3, -2, 0, then 5, then 3, -5, and there's a 0. So if we transpose this, A transpose, you notice we get 0, -2 with a 3. The row becomes a column. Then there's what? Okay, now okay. This is, let me say this. Let me see. Okay, that's then -5. The row become the column. So this stands up, comes there. This stands up. This stands up. That's going to be -3. Then 5 and a 0. Then we negate it. So get something like this. Yeah, so this, you notice that if you look at this matrix here, the one that we've negated, it's now exactly the same like the original matrix. This part here, yeah, this guy here that we have is exactly the same as this. So check this and that, they're the same. The content here, the entries. Without negating A transpose, we wouldn't have gotten A. Yeah, so hope you're able to see this part. Yeah, so that's what we mean by a skewed symmetric matrix. That's what we call, that's what we have. Now there are certain properties as well that should be satisfied. So the reason why you have to learn these properties is that sometimes they'll ask you to make up a matrix that is skew symmetric. It has to be in such, so you'll be, everyone makes, right? Everyone is going to have a different choice of numbers that they're going to use, but they're all going to be guided with the following properties. The first one, I'm sure it's common by now. It's supposed to be a square matrix. That's the first property. Meaning the number of rows should be the same as the number of columns. The second thing is that the equality, the negative equality between the original matrix and the transpose has to be satisfied. This has to be true as well. If it's not true, meaning it's not a skew symmetric matrix. Then we need to have 0 diagonal elements. So you see, there's a guidance. Because combination using this is the guidance. So they're saying the entries on the major diagonals are supposed to be zeros. It's easier that way. Yeah. Then the other one here, we're just saying, the fourth one, is that the sum or difference of skew symmetric matrices is also a skew symmetric matrix. So if you add A, so if A is already satisfying the fact that it gives us this, and B is also satisfying the fact that it gives us this, it means that when you add A and B, when you add A plus B, it will be the same as you adding this guy and this guy, which is negative A, this minus B, that which is the same as negative A transpose plus B transpose. So I'm sure this is, yeah, this is what we're supposed to get. Yes. Yeah, so hope this is okay here. And then we know what this is. Yeah, so we know what this is going to give us, the same as what this is going to be. We could have factorized the negative. So this is the same as, some people would say negative A is the same as here. Let me use a different color so that you see what I'm talking about. Instead of saying A is equal to negative A transpose, some people say negative A is equal to A transpose. You get, even here we'll say negative B is equal to B transpose. So that when you add these sides, they'll carry a negative now. negative A minus B is equal to AT plus BT. So this will factorize a negative. This is going to give us that, which is AT plus BT. So this is just us still trying to explain that the addition or subtraction of two skew symmetric matrices, the answer is also skew symmetric matrix. Yeah. Is this okay here, Chris? Do you need an example for this? Can I give an example? So we just look at the properties. Bakambache, the major key thing you need to focus on is what can you come up with first. So we need to come up with a matrix whose number of rows and columns are the same, and the major diagonal is what? The elements are going to give you zeros. So let's come up with something. So let me give an example. So it's a trial and error thing. It's not that you get it right at first. Probably you would, but we need to check. If I give you this, let's say I can give you any number. So let me use 0, 2 so that you just see what I'm talking about. Then let's say you have a 2, 0, and let's say there's a 5 there. Let's say 6. Is this true? No, the numbers here have to be the same. Yeah, so that we can flip them. So this has to be 3 to just differentiate it. So one has to be negative, one has to be positive. It's like they're pairs of some sort. How can I say this? There should be a 5 here, then a 0 there. Because we said the major diagonal entries must be 0. So you notice what I've done is put similar numbers because need it to be the same. When we flip it, the only difference will be in the negative. Yeah, so I'll put this one here to carry negative. Then I'll alternate it. The next guy to carry negative will be from this guy, the minor diagonal. Then the last here will be this. So that when you flip it, it will be 0, 2, negative 3, negative 2, 0, negative, a 5. Then there will be 3, negative 5, and a 0. So that when you multiply this with a negative, this now changes and becomes 0, 2, negative 3, negative 2, 0, 5, 3, negative 5, and a 0. You notice this is the same as A, satisfying the main property of skew symmetric matrices. Any questions here, Chris? Are you okay with this? Okay. Yeah, okay. So if this is fine, we can proceed now to look at orthogonal matrices. Yeah, so now all these small things that we are looking at, we'll need them later on in proving certain theories. So when I come back at orthogonal matrix, they assume that you already know. You get that because you've learned it here. So yeah, that's the reason why we're learning this. So when we're talking about orthogonal matrix, we talk about a matrix whereby if we multiply the transpose of that matrix and itself, we should get an identity matrix. That's what we mean by an orthogonal matrix. So it could be the other way around. We can multiply the matrix and its own transpose. We get back what? The identity matrix. Now, the A2, of course, is the transpose. I is the identity matrix. And now this condition is going to imply that this can only happen if A transpose is the inverse of that matrix. So this brings us to a concept of inverse. So this is true, this principle here, this is true if and only if A, the inverse of A is equal to the transpose of A, because whenever we multiply a matrix and its own inverse, that's the only time we get the identity matrix. So we're saying for this to be true, it means that this part here actually has to be the inverse. Now, how do we get the inverse of a matrix? We're going to learn that already. Okay, let me give an example here. How can I say this? Okay, I'll use something that's very straightforward. Let's say we need a square matrix for starters. How do you get the determinant of a matrix, Chris? Chris, mathematics attend my class. Oh, okay. Okay, so it's going to be major diagonal minus the minor diagonal. Yeah, so we just need to add these multiply. So if I give you A is equal to A, B, C, D, the determinant of A is equal to AD minus CB. Yeah, that's how we get the determinant of A. Yeah, so according to what we've done here, according to this example that I've picked, the determinant is just going to be 2 by 1 minus 3 by 1. So the answer is a negative 1. Then for you to get the inverse, we say the inverse is equal to 1 over the determinant of A multiplying the original matrix. That's what we have, which is a 2, 1, 3, 1. So this is going to give us 1 over negative 1. That's going to give us 2, 1, 3, and 1, meaning the answer is just going to give us a negative 2, negative 1, negative 3, negative 1. That's the inverse. Now if you try, we're saying this should give us the identity matrix, right? We expect to get 1, 0, 0, 1. That's the identity matrix for a 2 by 2, right? Yeah. So we're trying to multiply this matrix here and the original one. So let's check. So A and A inverse, that's going to give us, there's a 2. How can I say this? Is this true? Is this true? Let me just check this. Okay, just a minute. Let me see if what I'm doing is right. I think we're supposed to change this. We're supposed to multiply 1 over the determinant times the transpose of the matrix here. Let me remember what was happening in high school. Let's see. Oh yes, so yeah, this is what we used to do here, Chris. Sorry, I'd forgotten this. So we've gotten the determinant. The determinant is a negative what? Is a negative 1, yeah? So the determinant of A is negative 1. We want to get the inverse, right? That's what we want to do. Yeah, so the inverse is going to be, we used to say we switch the elements. So I want to get the inverse. Let me just do a recap here. Yeah, just a minute. Yeah, so inverse, if you want to get the inverse, let's say A inverse, this is equal to 1 over the determinant of the matrix. Then you're supposed to switch the major diagonal entries. Yeah, so switch the major diagonal entries, you switch these up. Then you multiply the ones in the minor diagonal with a negative. Yeah, so like the one that I had given us, they say this was what? 2, 1, 3, 1. Yeah, the determinant of A is negative 1. Then we're going to switch these guys here. And so to get A inverse, we'll say 1 over negative 1. So we switch 2 and 1. That's going to give us 2 and 1. 1 and 2. 1 and 2, yeah. This is for a 2 by 2 matrix, by the way. It will be different when we talk about a 3 by 3 matrix. Then the entries in the minor diagonal are going to be multiplied by a negative 1. So this is going to be negative 3, then negative 1. Yeah. Yeah. Then from here now, this is a negative 1. Then this is going to give us 1, negative 3, -1 and a 2. Then we multiply with this -1. That's going to give us -1, 3, then a 1 and a -2. So this is the inverse. Is this okay here, Chris? Or you need me to do another example? So this process here for an inverse only applies for a 2x2 matrix. For a 3x3 going up, you guys only end up to 3x3. I will show you how we get the inverse. Yeah, so this is okay though, right? Yeah, so I just want to confirm the property that we're talking about. We've said if we're dealing with such a matrix, we need to be able to get if it's an orthogonal matrix, when we multiply it and its own transpose, it gives us the identity matrix, implying that we say this, when we multiply this, it gives us the identity matrix, implying that this transpose is supposed to be equal to the inverse function. I mean the inverse matrix, sorry. So if I get my original guy, which is 1, 2, 1, 3, 1, let's try to multiply this. We need to get a 1, 0, 0, 1. So let's see if this is true. So it's row by column, right? 2 times -1, that's -2, plus 1 times 3, that's just a 3. Then again, row by column, that's going to be 2 plus -2. Then again, row by column, that's going to be -3 plus 3. Again, row by column, that's going to be 3 plus -2. So this is going to give us 1, 0, 0, 1. Yes, which is the identity matrix for a 2x2 matrix. Yeah, so this is perfect. This is okay. So we're on the right track here to say if here, well, I was giving an example. We're here. Yeah, we're saying if we multiply this guy, the transpose of A and A should get the identity matrix, meaning A inverse is equal to A transpose. That's going to give us what? That qualifies to be an orthogonal matrix. Now, how can we come up with an orthogonal matrix? There are certain properties we need to know. Again, properties that orthogonal matrices satisfy. The first one I've already given us to you. This is that, or AT, A is equal to that, if and only if the inverse is equal to the transpose means the inverse. So that's what you have. The second property is that every orthogonal matrix must be a square. Again, we're saying the number of rows has to be the same as the number of columns. Yeah, it has to be a square. Yeah. Then the determinant has to be plus or minus 1. So an orthogonal matrix. So if you're asked what's an orthogonal matrix, you have to write an orthogonal matrix is any matrix that satisfies the following properties. You start listing them. 1, the way we've listed them here. A, where A is a matrix. Yeah, so you say a matrix A is said to be orthogonal if and only if, then you list these properties. Yeah. Determinant, so we say determinant of A is either plus or minus 1. That's an orthogonal matrix. So it's supposed to be a square matrix. Yeah, then 4. Is there any other property? Okay, so here they just give us this guy here. Yeah, they just give us this. Then what do we say? Okay, the proof here. Oh, the fourth one is that the product of 2 orthogonal matrices is also going to be an orthogonal matrix. Yeah, so these are things that you need to master. I'll prove this one here. So let me write product . So proof for the last property, I'll give you proof here. Yeah, so if you have two matrices, we say that we say suppose A and B are orthogonal, right? It simply means that A transpose and A give us the identity matrix. Also B transpose and B also gives us identity matrix, right? That's what we're just having. Then remember, there's that property we said that if you have what? There's a property we said if you have AB multiplying each other, is it AB plus each other, then they'll give us we'll change the product of what? We said recall, so I'll say recall that AB transpose is equal to B transpose and A transpose. So remember this property, we talked about it when we were discussing the properties of what? Of transpose. Yeah, transpose matrices. This property was listed there. So now if this is true, remember we said A, B, that is equal to B, this, and AT. You already have this. It's a property you learned. So if I multiply this side by AB and also multiply this side by AB, what I've done is the same. So I've just introduced a new product here, which is AB. What we do on the right, we also do on the left. The reason being is that we said we can rearrange these guys in such a way that we said what? We said each of these, whenever you multiply AT, so how can I say this? This can be what? I'll get can I get the left or get the right? Okay, so I'll say since, remember we've said this again, AT and A, whenever you see A to the power T and A, we get the identity matrix. And also when you have BT and B, you get the identity matrix. The next step we're going to write is hence. Remember this, treat AB to the power T and AB as if ni matrix imos. So treat this is like so hence let me show you, let AB be equal to M. So this is the same as what? Where there's AB, I'll put M everywhere. So hope you're okay with me saying M to the power T and M is equal to this part. Look at this part. This is equal to 1, right? Remember, we said the product, if A and B are orthogonal, it means even their product is also orthogonal, right? So M is orthogonal. Now, if something is orthogonal, we said that same matrix and its own transpose should give us what? Should give us the identity, not 1. Sorry, this is an identity matrix. Yeah. Now, this identity matrix is also equal to this part. Yeah. So the only part I was trying to solve is the left-hand side, this part, which has given us 1, because I've replaced here with M and M. So you see this gives us that, meaning even the right-hand side as well. Even this part is also an identity matrix, because this is just like you saying M, T again, because these two things are the same. So if this is 1, meaning even this thing is 1. So yeah, that's how we check, or rather that's how we prove that it's an orthogonal matrix, because it's the original matrix and the transpose is also what? Giving us an identity matrix. So here again, I'll repeat this. When you multiply two orthogonal matrices, you also get an orthogonal matrix. Then the last property is that we have what you call symmetric orthogonal matrices. Remember what we talked about symmetric, meaning the matrix itself and the transpose are supposed to be the same, right? Those properties we discussed. So here we're mixing them now. Here we're saying the product of two, the two orthogonal, symmetric orthogonal matrices are the identity matrix, or it's negative. So let me write it here. Not. So 2200 if nikachewa iverenga daily, because tumaruzi ntwambiri na tumaprove tofu nukos what. Yeah, so if you'll be taking time to study it, you'll be forgetting things and you have to be going back afresh all the time. So personally, the reason why I did well in 2200 when I was taking it is because I used to practice on a daily basis. Yeah, because at least you guys don't have labs or anything, so meaning you have enough time Mukachoka class, if anything, just try, as soon as you're done with the class, kupita to my definition. That's the best way if you want a really, really good grade. Yeah, timvela na Kriska. Yeah, kutupita mche osaleka manoti ya sasa. Yeah, if you really want to do well, but ngofuna CR, then it's okay. You can put it to skip days like that. So here we're saying symmetric orthogonal matrices are the identity matrix or negative matrix. So matrix or identity matrix. Yeah. So what we mean is that if you give you, let's say, if A is both symmetric and orthogonal, then A must be an identity matrix or it's negative. Specifically, if A is symmetric and orthogonal, so we're saying if you find one matrix that is both orthogonal and symmetric, satisfying conditions yapa orthogonal and yapa symmetric, it means that A is equal to an identity matrix, or it's equal to negative the identity matrix. That's what we basically mean. Yeah. So this is, how can I say this? This can be shown as follows. So proof. How can we show? So the question can come as, show that an identity matrix is both symmetric and orthogonal. So how do we show? That's the proof I'm trying to do here. So the proof is that we have two conditions that should be satisfied. For a symmetric matrix, we said the matrix has to be the same as its own transpose, right? That's what we said. That's for a symmetric. Then if it's orthogonal, we said its transpose and the original matrix should give us what? The identity matrix. That's what we said. Right? So this is what we're having. So now we're trying to combine these guys. So how can I say this? So upper, look at this guy here. We are saying A should be equal to AT squared. So meaning pali AT squared upper, ningafakepo A, because even the same te from this thing, meaning A ngabwele actually replace up. So as color A and A. You get ka? So this is going to give us I. Now we have, this is the same as A squared. So A squared is equal to I. Right? Now if you square root I here, square root I, this is just going to give you A is equal to positive I, positive I, or A is equal to negative I. That's the reason why we have two alternatives. Yeah. So the only matrix that can be both symmetric and orthogonal is negative an identity matrix or just identity matrix. And this has to be, we said identities only occur or exist for square matrices where both the rows and the columns are the same. Yeah, so hope that's okay. There's a proof here, there's an example they gave, but then I'll skip it and go directly to another type of matrix. Yeah, which is just what? A zero matrix. Okay. So your task, I'll just say task, I want you to check if this guy here is an orthogonal matrix. Yeah, so proof, check that. So you're going to just show me that A, we said orthogonal matrix that when you multiply A transpose and A, we should get this guy. So the A matrix that you are given here is 1 over root 2. So you multiply this by its own transpose. There's a scalar outside, so I just want to see this. Okay, so in case there is, I think I've seen Charles trying to join in the group. I mean the link. I think let me just do 2200 today, so at the series I finish all my target. Yeah, so that we can do 2100 or just the whole lot of 2100 mile of foot. Yeah, so I want you to check this property here, the transpose of this. So you have to multiply the 1 over root 2 mkatum. So it's a boinkale 1 over root 2, negative 1 over root 2, then you have 1 over root 2, then you have 1 over root 2. So multiply this by its own transpose. See if it's going to give us an identity matrix. So you can do this at your own free time. Can we continue, Chris, or you're tired? So apart from the matrix which can either be symmetric or diagonal at the same time, which can either be equal to a negative identity matrix or the original, we said there are only two types of matrices that can be both symmetric and orthogonal, either a negative identity matrix or the original identity matrix of any square matrix, either 2 by 2, 3 by 3, 4 by 4, those things. So now we need to progress, talk about a zero matrix. So a zero matrix is just a matrix that has we say what, all the elements, all the entries are just zeros, and it's noted by letter O with M and N. It's not necessarily that it's supposed to be a square matrix. As long as it has zero entries everywhere, it's a zero matrix. It can either be a 2 by 3, so those things we need to put them into consideration. All the entries, so all entries are supposed to be zeros. Cons and my zeros, that's what we call a zero matrix. It's very easy. So this is straightforward. The axioms are very, very straightforward as well. We say any matrix plus a zero matrix is always going to be that same matrix. Then we can say what? Any matrix times the zero matrix always give us a zero matrix. That's obvious. Any scalar times the zero matrix is going to give us a zero matrix. So you can dot that times. Is there anything else I need to add here? No, this is multiplicative addition. So we have this. So zero matrices are unique because they are transposes. When you transpose them, they should give us that, right? So we have these four properties. It's obvious, I know, but we just need to look at them. Trace, I already explained what a trace of a matrix is. It's always going to be the summation of all the major diagonal entries. And I said in an event where a matrix is not a square matrix, where the rows and the columns are not the same, we cannot have a trace. So it has to be a square. So I cannot give you this and ask you for a trace. You tell me we cannot get a trace here because palibe major diagonal up. It's not a 3 by 3 or 2 by 2. This is what? This is a 3 by 2, right? So it's not a square matrix. Inverse, I've already explained how we get it. Mostly, maybe I need to talk about the properties of an inverse. Do we need to talk about? So every matrix has a particular. So we talk about the uniqueness. Okay, this is okay. I can skip this. Okay, so I need to talk about we're on what? 1.29. We'll talk about upper triangular matrix. So end here. So when you talk about an upper triangular matrix, we talk about a matrix which is a square matrix where all the entries below the major diagonal are simply zeros. That's basically what we mean. So it's supposed to be a square matrix. So let's say I give you something like this, A. We don't care what's here, but here there should be a 0. Then here I have, let's say, D. Then I can have anything here. Let's say E, 0, 0. Then I can have K. You see this? So all the entries down below the major diagonal must be zeros. So the major diagonal are these guys here, right? Remember what gives you your trace. So the entries down, these guys here down, are supposed to be zeros. A good illustration is if I give you 4, 3, 2, that's 0, 5, then I get 6, 0, 0, then I get 7. This here is an upper triangular matrix. So a non-example is if let's say there was a number here, let's say this is a 9, meaning that's not an upper triangular matrix. All the digits down there, the major diagonal are supposed to be 0. All the entries down below the main diagonal are supposed to be 0. That's what we call an upper triangular matrix. Now there's a way that we can come up with an upper triangular matrix, but then for the sake of today's class, we'll just end here. Then we'll continue to talk about properties of upper triangular matrices, then proceed to lower triangular matrices, just opposite, meaning everything above the main diagonal is supposed to be 0 entries. Yeah, we'll do the proofs that are necessary. Then we'll continue to talk about what polynomial expressions that involve matrices. How do we get polynomial expressions? Then the last thing that we're going to summarize the whole topic 1 is row echelon form and reduced row echelon form. Yeah, okay, so we end here for today. Thank you so much, Chris, and those who are going to watch the recorded session. I'll see you guys in the next lesson, lesson 2.